let's talk about exponential functions. In order to do that, I'd first like to take a step back and review what we've talked about previously in terms of exponential growth, and then extend that to the idea of exponential decay, and then we'll follow that up by looking at some example questions. So first of all, what does it mean when we talk about exponential? What it really means is that in order to find our next y value, we need to multiply by some constant value. So we've seen before with linear equations, if I have a straight line, every time I go over one, I go up by the same amount. And that's our rate triangle that we've seen in grade 9 and grade 10. So every time I want to find the next y value, I add 1 to my x value and go up by some same number on my y value. When we've been looking at quadratics, we've seen that there's a special step pattern where if I start at the origin and go over 1, and then I go up 1, go over 1, and then I go up 3, go over 1, and then I go up 5, and so on. With exponential, it turns out we're going to multiply by the same number every time. So as my graph curves up, let's say if I go over and up and it's 1, actually let's say, oh, it's fine. Let's say we go up by, let's say our original value is 2. I'm going to multiply by 3, and our next value is going to be 6. Go over 1 and up, and I multiply by 3 again. So I'm going to be at 18. Go over 1, go up, and I multiply by 3, and I'm going to be at 30 plus 24 is 54, and so on. And I'll be a little bit more explicit as we go through our example in a moment, but that's the basic idea behind exponential, that we're multiplying by some value to find our next y value. We'll get there in a moment and talk about doing a test to check if something is exponential, but let's start with our equation. What does an exponential equation look like? An exponential equation is going to take the form y equals a times b to the power of x, where a, think about a is like the first letter of the alphabet. A is my initial or starting value. So that might be like, what was my population at the beginning, or how much money did I first have in the bank. B is going to be 1 plus the growth rate. So if I have a growth rate of 20%, so I'm earning 20% interest every month or something, then this value would be 1.2. Or if my bacteria triples every hour, then my B value is going to be 3. So here my growth rate is 0.2 or 20%. Here my growth rate, so this is 1 plus my growth rate. So 3 minus 1 is 2 is my growth rate. So 200% is my growth rate here. So just be careful. The B value itself is not the growth rate. It is 1 plus the growth rate. So let's erase our extra stuff here and just try to keep our note nice and tidy. So 1 plus the growth rate, and then my x value here. Sometimes we use the letter t instead, and that indicates how many growth periods have elapsed. So periods of growth. So if I calculate the interest every month, it's how many months. If my bacteria population is tripling or doubling or whatever every hour, that's my number of hours, and so on. Let's take a look at a specific example, and let's practice going from, so we're going to go from equation to a table of values to a graph. And this is very similar to what we've done with quadratics, except it's a different type of function or a different type of relation. Function and relation just means there's some equation connecting our x and y values, and there's a little bit more of a specific meaning, but for this course we don't really have to worry about that. So sometimes I will kind of interchangeably use the words function or relation or even equation. In our example question, let's take a look, and our equation is going to be y equals 3 times 2 to the power of x. Let's also describe in words what's happening here. So our starting value is 3. Starting value of 3. And on my graph, that's going to be our y-intercept. So when x is 0, that's our y value. And 2 is our it says how much our our population or whatever is going to grow each time. So it's 1 plus the growth rate. So b equals 2, b equals 1 plus the growth rate. So so growth rate is equal to 1 or 100%. So what that means is after each period of time has happened, my population has increased by an additional 100% or it has doubled. So our growth rate is 100%, but basically we could say our value doubles in each period. And x is still a variable, but my x tells me how many doubling periods have occurred. Number of periods. Let's make a table of values. With a table of values, we are choosing some x values. So we're just going to choose basically some random numbers that are close to 0 and nice whole numbers just because they're easy to graph. I could choose any number I want. I could have negative 3 million and a half. I could have 975 divided by 13. I could have 12. But, it's going to be hard to make a graph big enough to fit those kind of numbers. So we want to keep it simple. And for exponential functions, we generally don't care about the negative values. So I'm going to start at 0. So I'm just going to choose some numbers, nice and tidy. I'm going to start at 0. And then our life is a lot easier if we go up by ones. So I'm going to have 0, 1, 2, 3, and 4. And so just to review, what do we do when we're working with an equation? X is my input. Those are the values that I choose. I put them into the equation machine where it does a calculation. And in this case, the calculation is y equals 3 times 2 to the power of x. And then my y value comes out, and that is my output. So I choose values for x, just a few specific ones, and then I can plot them on my graph and connect the curve and all that good stuff. And when I'm doing my table of values, when I want to find my y values, I just pick an x value, plug it into the machine, find the y value, and then I write it in the table. So let's go ahead and do that. I'm going to show my work. I guess I can leave the machine diagram up there. I think it's out of the way enough. So let's show our work just to start. So I'm going to take my equation, 3 times 2 to the power of x, but instead of x, I'm going to write my actual x value, which is 0. And remember, use your order of operations when you are solving this stuff. Ignore the 3 for now, and just focus on the exponent and the number it's being applied to. So the exponent and its base. So we're going to deal with the highlighted part first. 2 to the power of 0. That's one of the rules we learned about. Anything to the power of 0 has a value of 1. So 2 to the power of 0 is 1, and 1 times 3 is 3. And we'll notice that that's also our starting value. So when x is 0, y is our starting value, which is right there. So that looks good. That's what we expect to happen. So I'll just make a quick note that that's my a value. Let's find our next y value. What happens when x has a value of 1? What happens when our population has had 1 hour to grow? Well, we're going to write our equation, 3 times 2 to the power of x, but instead of x, I'm going to put in the actual number, which is 1. Once again, we're going to evaluate by first looking at the exponent and the base, and then multiplying by the 3 after. So 2 to the power of 1 is just 2, and 2 times 3 is 6. And we'll do our next one. And you don't have to show your work off to the side like this. I'm just trying to be super clear about the steps and where these numbers come from. If you just want to punch this in your calculator and find the y value is 6 and just write it in, that's totally fine. And then I will erase this later anyway, because I'm going to need the space for some other steps. So let's try again. I'm going to take my equation. I'm going to plug 2 into my equation. So 3 times 2 to the power of, instead of x, I put 2. And focusing on the exponent first, 2 times 2 to the power of 2 is 4. 4 times 3 is 12. And our next value, write the equation. Instead of x, write the number. 2 to the power of 3 is going to be 8. And 8 times 3 is 24. And finally, when x equals 4, my equation is going to be, 3 times 2, and instead of an x, I put in the 4. And 2 to the power of 4 is 16, and 16 times 3 is 48. So I have a nice set of values. I know that when x has these given values, I know the y values. Or in terms of our problem, I know that we're talking about bacteria at 1 hour. I have 6 bacteria. At 3 hours, I have 24 bacteria, and so on. So all we've done so far is we've started with an equation, and we've produced a table of values. Once I have a table of values, I can make a graph. And so I'm going to make the graph, and then I'm going to take a step back, and we'll talk about how do I prove that this is exponential. So let's sketch our graph. Our x values are going to go from 0 to 4. So I basically only need positive x values. So that makes my life a little bit easier. So x starts at 0 and goes up to 4. 1, 2, 3, 4. My y-axis is going to go up to 48, so it's going to be a little bit harder to scale, but we'll do our best. So 48, I usually start with the biggest number and then kind of divide it in half. 24, and then divide those each in half again. 36 and 12, and I'll make a little mark in between, but I'm not going to write the numbers, just so my graph doesn't get too cluttered. Now remember, each of the values in my table is an ordered pair. So really this is describing the point 0, 3, and 1, 6, and 2, 12, and 3, 24. So you've seen this before. This is my x value, and then the related y value. So I think you know how to plot points. Hopefully you're feeling pretty comfortable with that. Otherwise, hopefully I've explained it in enough detail. And if not, if you're having trouble, just ask me some questions in class or send me a quick email. But let's try graphing this. So I know that when x is equal to 0, y is equal to 3. So when x is equal to 0, I don't need to move left or right. I'm just going to go up 3. It's a little tricky to measure because like my first line here is already at 6. So just kind of eyeball it, get it as close as you can, and that 3 point's going to be right about there. Next up, when x is 1, y is going to be 6. And we are graphing by hand, so it won't be perfect, but just try to keep it pretty tidy. When x is 2, y is 12. When x is 3, y is 24. When x is 4, y is 48. And there we go. We've successfully graphed our points. Now, because we're dealing with a continuous function, so it exists at every point. So even though I only calculated when x equals 0 and 1 and 2 and 3, it still exists between those points. I could figure out how much bacteria is there at half an hour or 2.359 hours. Any number is possible. And so that's why we can connect the dots, because that just kind of tells us, hey, I could have chosen any number. There is a value that exists for each of these points. So let's just connect our line. Once again, try to keep it nice and smooth. I'll actually show you the other way first. So don't do sharp points that with tight angles. That doesn't look good. That's not a proper representation. Try to make it nice and smooth and going through all the dots. And then we add an arrow at the end to indicate that that function, that graph, that curve does continue. And we should label it. So we'll just write our equation. Actually, our equation's right here in this diagram. So we can just connect them so it's clearly labeled. So hopefully that wasn't too bad. We've successfully gone from having an equation to finding a table of values to sketching the graph by hand. And we could use a tool like Desmos as well, and you're welcome to do so to double check your work. Or on some assignments, I don't say how to make the graph, so you're welcome to use Desmos and take a screenshot. But it's good for us to be able to do this by hand. Now I want to answer the question, how do we prove that this is exponential? Because I got this nice looking curve, but what happens when I go backwards in time? What if it curves back up? Because then that kind of just looks like a parabola, and then maybe it's just a quadratic where we just kind of covered up this part and didn't worry about it. How do we know? How do we prove that? So let's talk about our tests. To test, first of all, we can look at the equation, and our equation was y equals 3 times 2 to the x. And we know it's exponential right away because I have some number as a base, number base, and a variable, so a letter variable as our exponent. So it's called exponential function because that means that our variable is in the exponent position. Technically, I don't even need to see a number here. If I just saw something like y equals 2 to the x, or y equals 7 to the x, or y equals half to the x, these are all examples of exponential functions. So how do I know something is an exponential function? There's some number as the base and some variable, and in our case it's going to be x, or sometimes like t for time, but some variable as our exponent. So that's our first test. Our second test is kind of like our first difference test. So I think I'm actually going to rewrite our table here rather than erasing my work, and we'll do our test. So I'm going to rewrite that kind of right here. So blue will be for our test. And let's rewrite our table real quick so we know where the values came from. I'm just copying it down so I can work on it without destroying our original. 4 and 3, 6, 12, 24, 48. And previously we've found the first difference. So I would take a y value and subtract the one that came before. 6 times 3 is 3. And then I'd repeat. So I take the next one, 12, minus the one that came before. 6 is 6, and so on. That's not what I'm going to do here. Instead, for my exponential test, I'm going to find the ratio or the quotient between the numbers. So I'm going to look for the ratio of y2 over y1. Now what that just means is take a y value and divide by the one that came before. So let's add a column and let's calculate. So I'm going to do 6 divided by 3, and that's 2. And I'm going to do 12 divided by 6, and that's 2. And I'm going to do 24 divided by 12, and that's 2. And I'm going to do 48 divided by 24, and that's 2. And when this ratio is always the same, that means that we've proven that it's exponential. So let's describe that. If the ratio is the same, then this is exponential. And this ratio, does it look familiar to anyone? This ratio is our b value. So I just found the ratio. It had a value of 2. Well, this number is 2. This number is 2. That's my b value. And so all this is connected. So as soon as I look at this equation, I already know the b value should be 2. Or if I don't have the equation, if I only start with my table of values, then I can do my ratio test here. I can find this number, and that's my b value, and then I know this is my a value, so I actually have enough information to quickly find the equation when I'm dealing with exponential functions. This is actually a really nice feature of exponential functions, that it's really easy to find the equation from the table of values, because I have my a value, I have my b value, and the only other value is x. I don't need to solve for x. I just write x, and I'm done. So that makes our life nice and easy. It's a lot harder with, or it's a bit harder with quadratics or even linear functions. And so there's going to be a test we're going to do on our graph, but honestly, it's really just the same test we just did on the table of values. So there's no like step pattern to look for, but let's still kind of talk about it. But basically, we're doing the same test we just did here. So let's take a look at what happens. So my original y value is 3. So I go over 1, and I go from 3 to 6. So what did I do? To go from 3 to 6, I multiplied by 2. And then I go over 1, and I go from 6 to 12. What's the relationship? How do I go from a 6 to a 12? Well, I times by 2. And then I'm going to go over 1, and I go up from 12 to 24. How do I change a 12 into a 24? I multiply by 2. And I'm going to go over 1 and up 1 again, and I'm going from 24 to 48. And how do I go from 24 to 48? I multiply by 2. So in each case, to find the next y value, I'm multiplying by 2. So that means it's exponential. So I don't even really know what to call this. We'll call it a step pattern. It's a step pattern where each y value is a multiple of the previous value. So basically, in order to find the next y value, I take the y value before, and I multiply by 2, and I multiply by 2, and I multiply by 2. And if my b value was something different, it's only 2 because this specific equation is 2. If it was like a 3 or a 4 or a 5, whatever the number is, as long as I'm multiplying each time to find the next number, that means it's exponential. So what I really recommend doing is if I give you a graph like this and I say find the equation, well, then I can look right here and find my y-intercept, and that's my a value. And then I'm going to figure out what number I'm multiplying by each time. So really, I would just make a table of values. I would read the points off the graph. I would put it in the table of values. I would do the common ratio test, and find the b value that way. And we can work through an example of that in class if you like. All right, so that's our recap and a little bit of new information about exponential growth. I'm actually going to stop the video here and then make a separate video where we dive into the idea of exponential